So it just went out.
Did you send the slides?
Yes, I did.
Okay, because I haven't received them yet.
Okay. I can try again.
I'll go out of the room.
Different server.
Okay, Professor Alex, you can control
Yes.
the slides from your side?
Yes, I can. Like
okay,
this.
Perfect.
Yeah.
السلام عليكم ورحمة الله وبركاته. السيدات والسادة، السلام عليكم ورحمة الله. أسعد الله صباحكم بكل خير. نتشرف بحضوركم لليوم الثالث للمؤتمر السادس لعلوم الرياضيات وتطبيقاتها، ويسعدنا البدء بالجلسة الأولى التي ترأسها سعادة الدكتورة دلال الغانم، ويتحدث فيها بروفيسور ألكسندر شيد دكتور جامعة واترلو الكندية. Esteemed guests, ladies and gentlemen, good morning everyone. We are honored by your presence today at the third day at the 6th Conference of Mathematical Science and Applications. We are pleased to begin the first session chaired by Dr. Dalal Ghanem and featuring Professor Alexander Schied, Doctor at Waterloo University.
Good morning, everyone. Welcome to the session of this conference. We are pleased to have with us Professor Alexander Schied, who will be presenting on exploring roughness in stochastic processes. Professor Alexander Schied is the Munich Reed Chair in the Department of Statistics and Actuarial Sciences at the University of Waterloo. His research focuses on quantitative finance, probability theory, and stochastic analysis, with recent work on risk measurement and management, financial modeling, and optimization. Robustness and model uncertainty and market microstructure. He is co-author with Hans Follmen of Stochastic Finance and Introduction in Discrete Time. He currently serves in co-editor of Finance and Stochastic and sits on several other editorial boards, including Applied Mathematics and Optimization, Mathematical Finance, and the Siam book series of financial mathematics. Prior to joining Waterloo, he was a professor at the University of Mannheim. He held position as associate professor at TU Munich, Cornell University, and TU Berlin prior to that. He stayed at UBC and MSRI Berkeley with research fellowships, and he was scientific assistant at HU Berlin. He earned a doctorate in mathematics from the University of Bonn. Let's welcome Professor Alexander Schied.
Yeah, thank you very much for the kind introduction. Before starting, I would like to thank the Saudi Association for the Mathematical Sciences and Professor Mohammed Adabi for organizing this conference and giving me the honor to present my work here. This is a great pleasure for me. However, I regret very much that I cannot be with you today in person in Riyadh. The work I'm presenting is a joint work with two brilliant young students, Xie Han and Zhenyuan Zhang. Xie is now a postdoc with us in Waterloo, and Zhenyuan is pursuing a PhD at Stanford. So, and the work is evolving around the following question. So we take any non-constant continuous function, say little x. So this should be a function defined on the unit interval into the real numbers. And you could think of this function as representing a sample path of a stochastic process. It could also be a classical fractal function or an empirically observed phenomenon. And a question which has been asked for a long time, but recently received some increased attention in the context of stochastic volatility model is the question, how rough is this function? So what is a good measure for measuring the roughness of this function? And the traditional answer you find in the literature is that you should use the Hurst parameter of this function. So either defined via the stochastic process or for the function taken as an empirical time series. And this Hurst parameter is typically measured in through either autocorrelation or through rescaled range analysis. And this is, for instance, implemented also in the extreme Hurst function on the Bloomberg terminal. So this is something which is of significant practical importance. However, in a paper in 2004, Knighting and Schlatter showed that the Hurst parameter, when measured in that way, may be completely unrelated to the actual roughness of a time series if measured in terms, for instance, of fractal dimension. One knows that there is a certain relationship if the time series is stationary, but otherwise there may not be a relation. It may actually be completely unrelated. And so the Hurst parameter as a measure of roughness is not appropriate in all settings. And so what Xie Han and I have been doing is we have come up with an alternative measure for the roughness, which we call the roughness exponent. So let me explain what it is. So we start by taking a fixed refining sequence of partitions of the domain of our function of the unit interval. So that means for each n, Tn is a partition of that unit interval, and the fact that it's refining means that you have this relationship. So it's an increase. So the partitions are an increasing sequence whose mesh tends to 0. And for financial data, you may think of the following canonical sequence. You look at yearly data, you look at quarterly, monthly, weekly, daily, hourly data, all the way down to 1 second and 1 millisecond and tick data. We're keeping this refining sequence of partitions fixed. And then what we are doing is we are computing the p-th variation of the function x along each of these partitions. So we are summing up the p-th powers of the increments of x along the partition points. Yeah, so we take the increments of x, take the absolute value, put it to the p-th power, and sum over all partition points. And if there exists a cutoff point, a certain critical p, such that for p larger than this cutoff point, this limit here is 0, and for p smaller than this cutoff point, this limit is going to be infinity, then 1 over this cutoff point, the reciprocal of that cutoff point, is defined as the roughness exponent. So the roughness exponent being defined over p-th variations. And then we looked at the mathematical properties of this roughness exponent. But first of all, we can say that it's a simple and straightforward measure that can be easily calculated. So if you have this time series, it's actually pretty easy to calculate. It's not such as the fractal dimension being very difficult to compute. It's actually in most cases pretty easy, and this is what you would like to have from a roughness measure. Right? It should be easy to compute. It disentangles roughness from other notions such as autocorrelations. And we could show that this roughness exponent is related to, but different from, traditional roughness measures, such as weighted quadratic variation introduced by Gladyshev in 1961, base of regularity introduced and investigated by Rosenbaum, and many other properties. Now, if you are at this critical threshold, yeah, just in between these two regimes, where you have either convergence to infinity for smaller p's or convergence to 0 for larger p's, then the limit may or may not exist at this critical threshold. Yeah, so the limit would be the p-th variation. This may or may not exist. But if functions do have a continuous p-th variation, then it's known that they can be used as integrators in Edo calculus. So we know that, for instance, functions of bounded variation can be used as integrators in Riemann-Stieltjes calculus, but this actually extends to higher variations in a strictly pathwise way. So you can use Edo calculus in a strictly pathwise way without having to assume that there is an underlying probability space, that you have a semi-martingale, but just in a pathwise way, you can do this for p between 1 and 2, according to an old paper by Hans Follmen. And more recently, Konstantin Perkovsky did the work for all p larger than 1. The case r equal to 0 is possible, corresponding to a specific, particularly rough time series. So the smaller r is, the more rough the intuition is the function should look like. And there are functions for which r doesn't exist. Yeah, where you would get here of these sums a lim inf and a lim sub, which could oscillate between 0 and infinity, leading to an interval of possible p's here in this identity, and that would correspond to multifractality in some way, right? So let's look at a few examples where this R can be computed. So first of all, if you have a function of bounded variation, then you have R equal to 1. Yeah, so this is, or a smooth function. So this is R equal to 1. This is the largest possible value, and this is the smooth case. The converse is, however, not true. There are functions with R equal to 1 which are nowhere differentiable. Then if you look at semi-martingale trajectories such as Brownian motion, you always have R equal to 1/2. So corresponding to the fact that you have finite and non-zero quadratic variation. And if you go to the class of fractional Brownian motion, in this case, R actually coincides with the Hurst parameter. So in this case, actually the Hurst parameter is a good measure of roughness if you restrict it to fractional Brownian motion, simply because it coincides with the roughness exponent. And here you see, so for the Hurst parameter, which is equal to the roughness parameter of 0.1, you have a very rough time series, which is highly mean reverting. On the other hand, for H equal to 0.9, you have a trending trajectories. You have trending trajectories with very little roughness. And in the middle, you have H equal to 0.5, which corresponds to standard Brownian motion. Now, as another class of examples, we look at classical fractal functions. So take a function phi, and this should not be on a 0, 1. This should be on the entire real line. This is, let this be an Lipschitz continuous and one periodic function. So it should have a period 1. And then we are looking at the function f of t defined in this way. So we are taking we're taking an integer b, which is larger than or equal to 2, take the nth power of b, multiply this with t, and apply it to the function phi. So this would be, since phi is one periodic, this would be the same thing as phi applied to the fractional part of b to the m times t, if these bracelets indicate the fractional part of a real number. And so through the fractional part, some chaotic behavior comes into this function, if you will. And so you're summing this series up weighted with alpha to the m, where alpha is between -1 and 1, and of course non-zero. So this is a class of functions which includes, for instance, the traditional Weierstrass functions introduced by Karl Weierstrass to get functions which are continuous and nowhere differentiable, which happen if you take for phi a trigonometric function, and the Takagi-van der Waarden functions introduced by Takagi and van der Waarden for the same purpose as Weierstrass's functions. In this case, you take the tent map. So this is basically just the function which goes up and down like this. And for those functions, we have a small theorem under certain mild conditions, which are satisfied by the trigonometric functions and the tent map. We can compute the roughness exponent of this function f here. Namely, it's given by the minimum of 1 and minus log absolute value of alpha to the base of b. This is the roughness exponent on the b-adic partitions. So here Tn is simply b to the -nk, where k goes from 0 to b to the n. And this is actually a deterministic result, but the proof is probabilistic. So the proof uses actually some martingale type arguments. Yeah, but it's a purely analytic result. And this result inspired us to construct a new class of stochastic processes, namely the so-called Weierstrass bridges. So, and the idea is the following. So in this, the Weierstrass type convolution, which led us to the function f, the fractal function f, we are replacing this function phi, which is one periodic, by the periodic continuation of a fractional Brownian bridge. So this, Brownian bridge basically means we are taking a fractional Brownian motion, but then we are forcing it to be at time 1 back at 0 again, so that we get some kind of periodicity, right? So we are starting at 0, we are going back to 0 again, and then we are just pasting this function behind itself and get this type of function here. And now we have basically a stochastic process as a function of t defined on the unit interval. And to get a fractional Brownian bridge, what we are doing is we are taking a fractional Brownian motion WH, and we are subtracting a function kappa t times the terminal value of h, and this function kappa t should of course be 1 at 0 and 0 at 1. And what if one takes, for instance, this function kappa t here, then you actually can show that the law of this bridge process here is, at least informally, that of the fractional Brownian motion conditioned on being at 0 in time 1. And so with this definition, which we can now, instead of having to paste the Brownian bridge behind each other, which we can also rewrite with the fractional part of b to the m times t, we get a new class of stochastic processes called the fractional Wiener Weierstrass processes. So, and this has parameters alpha, b, and h. And with these processes, we basically combine fractal geometry and fractional stochastic analysis. And now, of course, the question is, how rough is this fractional Wiener Weierstrass bridge? And what one expects is that there should be some kind of competition going on the one hand, between the roughness of the input of the fractional Brownian bridge, which is measured through this Hurst exponent h, and of the underlying fractional and of the convolution coming from this fractal construction, which leads to the roughness exponent k, which we had in the theorem beforehand. And so this is indeed the case. And we have the following theorem. So the roughness exponent is given by the minimum of h and k. So that is not very surprising. So whatever is more rough dominates the roughness here. And if we look at the critical p, so the p equal to the reciprocal of h minimum h, then we have some results on the pth variation of x. So if the k dominates, so if h is larger than k, then the 1 over kth variation is equal to a random variable times t. So we have a linear 1 over kth variation, as we would have for fractional Brownian motion or Brownian motion, but the coefficient is random. If the h dominates, so if the h is less than k, then we have a linear 1 over h variation, but the coefficient is now a constant, which we can compute in closed form. And the most interesting case is the critical case, namely h equal to k. And in this case, we can only say something if both h and k are equal to 1/2, because this is the most difficult case. And what we find is that the quadratic variation of x is infinite, but if we rescale with the factor 1/n, the quadratic variation, we find a quadratic variation equal to t. Rescaled quadratic variation is equal to t. However, this also shows that the quadratic variation of x is almost truly infinite. So it does not behave as either a Weierstrass function or a Brownian motion. So let me quickly go over a few properties of the fractional Wiener-Weierstrass bridge. And the difficulty, it turns out, is the covariance structure of this process. So to see what happens to covariance structure, let's look at the function CST, which is the covariance function of this process. Now, then let us introduce phi of t as in this form. So we are taking the covariance and we are subtracting alpha of the covariance S, where we replace t by the fractional part of b times t. And this function, of course, has the properties that at 0 and at 1, it's equal to 0. And if you expand this identity here, you quickly see that the covariance can be represented as the, say, Weierstrass convolution of phi. So the covariance itself has a fractal structure. And to see this even more clearly, we fix some even value b, and let's say h equal to 1/2, s equal to 1/2, then phi is by definition equal to this thing here. Then you compare the terms and you see the only difference is a +1 here in the alpha exponent. So you subtract the two terms, you get simply this thing here. But if s is equal to 1/2, all factors of b to the m times s for m larger than 1 are going to be integers. So the fractional part is 0. So b of h of this thing is going to be 0. So only the very first term remains, which gives us this expression. And for the covariance of the fractional Brownian motion is simply the tent map. So in this case, we see that C is actually a Takagi-van der Waals function. So we recover the Takagi-van der Waals function in the covariance structure of the fractional Wiener-Weierstrass bridge. And if you plot the covariance function C in 3D, you see you have very rough fractal covariance structures here, which actually have the same roughness exponent as the sample paths of x. And this makes the analysis of this process quite difficult because you have to deal with this fractal covariance structure all the time. As for a Gaussian process, the covariance structure basically determines the sample path properties. So nevertheless, we are able to get a few results. So for instance, we can show that the fractional Wiener-Weierstrass process is not a semi-martingale for any choice of parameters. If, under some restriction on the parameters, the Hausdorff dimension of the graph is equal to 2 minus h maximum 2 minus k for almost all sample paths. The leftmost position of the maximum is atomless if and only if the distribution, if and only if the roughness of the fractional Brownian motion dominates. Otherwise, it has an atom at 0. We can compute the Wiener-Young phi variation, and I'm sparing you the formulas because they're pretty long, and I want to talk about something else also later on. We can compute local moduli of continuity akin to a law of the iterated logarithm. We can compute uniform moduli of continuity, just as for the Levy modulus for Brownian motion. And what we find is basically we have three regimes. First, the regime where H dominates is similar to fractional Brownian motion. We get exact moduli of continuity with deterministic coefficients, which hold almost surely. For H larger than K, the behavior is similar to the fractal function, but we do not get exact moduli of continuity. So they will always involve random variables which are non-degenerate and unbounded. And in the critical case, we get some new behavior, which is neither like fractional Brownian motion nor like the Weierstrass function. And we get exact moduli of continuity. So this is essentially the high-level description of the result we have here. So so the proofs rely on representing the increments in terms of Wiener integrals, and then externalize the quasi-random behavior of the fractional parts via auxiliary random variables, and then apply results and techniques from Gaussian analysis. Now, in the remaining time, I briefly want to talk about something completely different, namely the model-free estimation of the roughness exponent, which is actually the original motivation for this work. Namely, we return to the general setting from the beginning. We have a function x, which is defined on the real line, is non-constant, and it's observed at discrete times. So, for instance, we are saying we are observing it along the dyadic partition of degree n. So we are observing all those points here. And now we want to compute the roughness of x from these observations. And this is the practical type application. So the dyadic partition can be represented by replaced by something more complex, but the formulas are particularly easy in this case. And this boils down to working with the Faber-Schauder functions, which is basically a wavelet series for continuous functions on R. So you're starting basically from the tent map. This is the big one here. And then you're rescaling to functions EMK, which look like little heads. And every little colored wedge on this graph is another EMK. And so with these functions, you can basically then express linear interpolation of functions via a basis. And the representation of any function x is in the following way. So the function x, or the end linear approximation of x, can be expressed by an affine part, which is not of interest and which we are completely ignoring in the sequel. And then we are having a linear combination of all the Faber-Schauder functions, EMK, with certain coefficients, and the coefficients can be computed in closed form very easily from the function x. And then if you look at what the result is, you are basically getting the linear interpolation of a function, of a given function along the dyadic partition. So this is a very easy and convenient basis for linear interpolation. And using the coefficients theta introduced here, we can now define an estimator for the roughness of a given function, defined in this way. Yeah, so we are taking basically the L2 norm of the coefficients theta mk, then taking the log to the basis of 2 and rescale. And this is also known as the Gladyshev estimator. And for a Brownian motion, for instance, we know that the Faber-Schauder coefficients are all independent, identically distributed with a standard normal random variable. And then you see basically you have the log of this thing here this is the law of large numbers, which just tells us this goes to 1. So the 1/2 here is everything which remains because this log goes to 0. And so we get the roughness exponent of 1/2 for the Brownian motion by the strong law of large numbers. And then I'm introducing a condition, which is, so don't look too close at the formulas. It's a condition which we need for the following results to hold. This is a condition on the Faber-Schauder coefficients, and it's akin to a reverse Jensen condition. Yeah, I'm not explaining the details here now, but it's not a restrictive condition. We can show that the sample parts of fractional Brownian motion satisfy this reverse Jensen condition with probability 1, and that they admit the roughness exponent h. And it's also empirically benign. So here we are plotting basically what we need for the reverse Jensen condition for the 1-minute log prices of continuous E-mini SPX futures. And so for the reverse Jensen condition not to hold, this thing should grow exponentially. And this thing should decay exponentially. And you see it doesn't. Yeah, so this means that the reverse Jensen condition should also be satisfied for financial data. Yeah. And then we have the following result. So if the reverse Jensen condition is satisfied for a given function x, then this function admits the roughness exponent r if and only if the Gladyshev estimators of x converge to r. And conversely, if this condition holds, if the Gladyshev estimators of x converge to the roughness exponent r of x, then the reverse Jensen condition must hold at least at 1 over the roughness exponent at the reciprocal. So this is basically an analytic theorem because it applies to given continuous functions. But it can also be seen as a statistical strong consistency result, as it gives you a convergence result for an estimator applied to the function x. However, there is no probability behind this. It's a strictly pathwise consistency result, a strictly pathwise statistics result without any probabilities. The result also clarifies that the Gladyshev estimator, right, which was used in the literature. Sorry, is there a question? Which was used in the literature to estimate the Hurst exponent, actually does not measure the Hurst exponent. It measures the roughness exponent. And only if the two are equal, it measures the Hurst exponent. So it clarifies what this traditional Gladyshev estimator actually measures. Even though the theorem is sorry, I was hearing something. Is there a question?
Sorry, no, you can continue.
Okay, thank you very much. Even though the theorem is a deterministic theorem, the proof is probabilistic. It relies on martingale techniques, which are basically a martingale which is hidden in the Faber-Schauder development of a function x. And this comes to the fact that if you look at the Faber-Schauder functions and take their derivatives, you get the Rademacher functions essentially up to a constant. And the Rademacher functions are known to be a IID series of random variables on the backspace. And so the Faber-Schauder coefficients then act as, say, a martingale transform for this IID series. And what's also important is if you apply the Stolz-Cesaro theorem to the Gladyshev estimator, you can basically reduce the summation of the Faber-Schauder coefficients to the final generation only. So you throw away all previous generations, you can only use the final generation, which actually makes the things simple, and the consistency will also be given for this estimator. And if you are in the diffusive case, if you are in the diffusive case, so you have a function with roughness exponent 1/2, then the limit of the Gladyshev estimator will be 1/2, even if a reverse Jensen condition is not satisfied. So this is also simple. Then we can get in the probabilistic setting, for instance, for fractional Brownian motion, we can get convergence rates for this Gladyshev estimator, which basically improve results in the literature. And finally, let me take, oh, I see my time is almost over, so let me take just 1 minute to just basically announce what the entire endeavor was about, namely about the problem of estimating the roughness exponent of a stochastic volatility model. In a stochastic volatility model, the difficulty is that the volatility you're seeing here cannot be observed directly. All you can see is basically the quadratic variation of the solution of this SDE, which is an integral of the square of the volatility. So you are coming to the problem of observing an integral of a nonlinear distorted function x, and you're making discrete observation of this y, and you're trying to infer the roughness of x from the observations of y. And what one, for instance, could do is one could look at discrete observations of the y, then try to get the x by numerical differentiation, and then compute the Faber-Schauder coefficients, and then compute the roughness estimator. But this is a problem which doesn't work out, because noise introduced through this numerical differentiation can actually outweigh any signal. And so we proposed a new estimator for this, which can actually also be computed again in a straightforward manner from the observations of y. So we have these coefficients here, and then an estimator which is of this form, and we can show this estimator works actually well in this situation. So I believe my time is up. So I thank you for your attention, and I'd be happy to answer any questions. So yeah.
Thank you very much, Professor Alexander. Thank you. Anyone would like to have a question with Professor Alex?
Thank you very much, Professor Alexander, for your nice conference. I would like to know if you have tried to use some wavelet tools to recover some of your results.
Yeah, excellent question. Thank you very much. This is a very good question. So indeed, the Faber-Schauder series of functions can be seen as a particular wavelet expansion. There are in the general wavelet expansion, there are some phenomena which sometimes are observed in greater generality, which we could, in some sense, rediscover in our analysis if we replace the Faber-Schauder coefficients by a different wavelet basis. Maybe some results would still go through, but it turns out that the Faber-Schauder basis is actually a very convenient basis, in particular for quadratic variation, because there is a formula by Gantert which relates the L2 norm of the Faber-Schauder coefficients directly to the quadratic variation of a function. Yeah, so the two things are very closely related. So the Faber-Schauder coefficients actually fit extremely well to the quadratic variation. Now the question is, if one looks at p-th variation for a p which is different from 2, is there perhaps another wavelet basis which would relate directly to that particular p-th variation? This is something we do not know, but it could be helpful.
Thank you very much.
So, Alexander Schied for this nice talk. I have one question. Can you say something about multifractional Brownian motion, for example, when the Hurst parameter depends on time?
Oh yeah, this is also a very excellent question. I don't know. I probably don't have the slides here, but this is something which we are working on, which we have been working on. How to capture, say, a time-dependent Hurst parameter, a time-dependent roughness parameter, and this can be basically done by, for instance, in a naive way. You just take you have a long function, so say defined on say a larger time interval, and then you are kind of covering this time interval with shorter time intervals, and then you measure in each of the small time intervals, you measure the roughness exponent, and then you get basically a time-dependent roughness exponent. This is the naive way, which already works sort of okay. So we for instance, done this for financial data prices over longer time horizons. And what we found is, if you, for instance, look at intervals which are maybe a week long, and you try to cover a financial time series, then you can actually see that, for instance, before the financial crisis of 2008, the prices of the STX had a roughness exponent which went down even before the actual drop. So that's a very interesting phenomenon we could observe empirically. But to get the to get convergence results and so on, this is still work in progress for dynamic roughness exponent measurement.
More questions? I believe, Professor Alex, there are many applications in financial mathematics could be applied from your results, isn't it?
Yeah, so what I mentioned, what I just mentioned about the possibility of looking at financial time and looking at the time varying roughness exponent for financial time series. That's something we like to look at more closely. And also, of course, the original motivation was to give an estimator for the roughness of stochastic volatility, because there were some papers in the literature which claimed that the observed roughness of the stochastic volatility, as observed by Gatherell and co-authors wait, where is the paper? This paper here, this paper, volatility is rough. That this is actually just an artifact of the errors which are introduced, for instance, through numerical differentiation. And so our actually project was about finding a different way of estimating the roughness, so that we could actually reconcile this result and maybe apply it to financial data. So this is also something we are working on, but we have to, so there are some estimation errors which we have to take care about in a very careful manner, because it's actually quite, you have various approximations there. So first of all, you cannot observe volatility directly, and second, you even cannot observe the antiderivative of volatility directly. You can only observe an approximation to the antiderivative. So this approximation creates a lot of noise in the observation of a very delicate signal here, namely the roughness. And we want to be sure that we can actually handle this well before we apply this to data.
Okay. Thank you very much, Professor Alexander, for this interesting talk. And we would like really to thank you again for delivering this talk through Zoom. And we would like to have you and to be so honored to have you in person next time. Thank you again.
Oh, that would be great. Yeah, thank you very much again for the invitation. I'm honored being a speaker at your conference. And again, I regret so much not being with you here. So actually we have outside, we have -degrees currently in spring. So it's been snowing a little bit in the past days. So still very cold. And yeah, I believe you have sunny and warm weather in Riyadh. So yeah, I wish you the best success for the, and thanks very much again.
Dr. Alex, if you would like to attend the other talk, you can continue on the same link.
Okay, I will.
If you prefer.
Thank you.
Okay. Thank you. Bye-bye now.
Bye-bye. Thank you.
But now let's move to the second talk. It's my pleasure to introduce Professor Manuel Morales, who will be speaking on the topic building a university-based knowledge transfer network for the financial sector, the case of Fin machine learning. Professor Manuel is the professor at the University of Montreal, working in the field of applied artificial intelligence in banking and investment, with experience in creating business value through machine learning and AI, an active member of the Montreal AI community, involved in various collaborative initiatives linking up R&D teams with product owners, managers, in order to create a coherent AI transformation strategy, including robust governance structures for AI systems. During his work as chief AI scientist at National Bank of Canada, the sixth largest commercial bank in Canada, he oversaw scientific component of the AI transformation initiative. More recently, he took on a role as digital strategy and innovation advisor at BSP Investment, one of Canada's largest pension investment funds with over 280 billion assets under management. As a researcher affiliated with OBVIA, he is also involved in the ongoing worldwide discussion around AI ethics, a commitment to responsible AI deployments, currently working on the impact of AI measuring and reporting ESG footprint in the context of sustainable finance. He is active member of the FinTech community in Montreal, where he plays different roles as advisor and founder. Please join me in welcoming Professor Manuel.
Hello, can you hear me? Yeah. Well, thank you very much for the introduction, the very nice introduction, and I'm honored to be here. As you may have guessed by looking at my abstract, you will see no equations in my presentation. Maybe I need the mic. Okay, I guess now it's better. And the clicker, oh, I can do it from here. Yes. Okay. Okay, so like I said, you will see no equations in my presentation, but I think I wanted more to tell you a story of how in Montreal we build a network, a training network with various universities with the goal of creating more opportunities for students with collaborative research and help our students get more exposure to the actual real problems in the industry within the financial and insurance sector. So I think that's a very nice story. It's a story about knowledge transfer, which I think might be interesting for some of you here. Because talking with my colleagues here, I understand there's a transformation within the university and trying to target new ways of creating opportunities for students. So I thought it was very, very timely maybe to talk to you about this things that we've been doing in Montreal. So that's my goal today. So maybe a little bit more context. So in my previous life as a researcher, I've been doing research affiliated with the University of Montreal for the past 20 years. Maybe the first half of those 20 years, I was focusing on stochastic processes, a little bit with the same flavor as Alexander Schied, my colleague from Waterloo, was doing today, working on the theoretical aspects of stochastic processes, always within the financial perspective. My research slowly shifted towards more applied side of it. So how do we estimate those processes? Then I started collaborating with National Bank of Canada, which is a private bank. It's not the Central Bank of Canada. It happens to be named national, but it's a private bank. And there I found a team of PhDs and master's students working on high frequency trading. So for those of you who haven't heard of it, it's just trading, but that happens, orders happen at the level of nanoseconds, microseconds. And then we started trying to bring the mathematical finance frameworks to see if we could help them maybe make better decisions and improve on the risk management or on their P&L, the profit and loss profile. And then slowly we shifted towards more looking at the data, because when you are in that world, like at the nanosecond level, you just have so much data, volumes are huge. And then there's more structure that we can get from the non-parametric approach. So that led to machine learning models. And that's where the AI label started to appear in those works. So that's a little bit of my journey. Then after leaving National Bank, I came back to university at a time where the university was looking for a way to handle the interest coming from the industry towards the research that was being made at the university. And we did some interesting stuff. So we created an institute. We created a network, Follmen network, which stands for Finance and Machine Learning. And I'm going to tell you about the story of how we did this. Hopefully you will find that interesting. So, and then also at the end, I will talk a little bit about the kind of projects that we were doing within this framework, because it was not only about knowledge transfer, it was about research, collaborative research. So there were very interesting projects, more than 200 students coming out of these projects with degrees, PhDs, masters, maybe close to 300 projects. So actual projects, when I mean projects, I mean teams of researchers, students funded by private sector and public sector. So interesting way of orchestrating things. So IVADO stands for the Institute of Data Valorization. So it's not a research institute. It's more an umbrella, a federating institute that under which existing institutes that do research, and I will show you the logos, can find support to connect with partners in the industry, support on the data side as well. How do you handle the data, clean the data? We know that when you're doing research in applied field, just cleaning the data and working with that, it's a heavy lifting. And also all the burden of having to go through the agreements that you need to have in place to have this kind of projects with industry. Those who have tried it, you know that before you can even start the project, it takes a long, long time to set it up. And so IVADO is this umbrella that helps researchers go through this and scale the number of projects we have. So it's building, of course, on a foundation that we had in Montreal, more than 40 years doing mathematical science, operational research, and computer science. It's building on 7 research centers and 3 universities within the city. But what it is, it's a bridge. So like I said, it's a well-funded, and I will talk more about the funding, institution that has its own team, not a research team, but a support team to do collaborative research, training programs, and as well to connect with the community. When I mean community, I mean students, but also partners. So there are industry partners around this institution. And this is this is larger than finance. As you will see, it's building bridges across many sectors. So like I said, it happened. I will tell you a little bit about this story. So it was built on a foundation structure that we had in place. Montreal has been well known for deep learning and operation research for years. But then, if those of you who have been following this, deep learning has been around for more than 50 years. And it was just one of many techniques within the machine learning framework. But then around 2012, 2014, it happened that the first neural networks, very large neural networks, were trained. And then that's where you could start seeing very successful applications on image recognition, text recognition. And that attracted a lot of attention from big players, Google, Facebook, and also large financial institutions who were wondering if they could use this technology to their benefit. And so they started approaching the university. And one interesting thing, maybe the first takeaway of this, is that this was recognized early in this story. So we're talking about 2014. So the first successful applications of neural networks were around 2012, 2013. So in 2014, the government of Canada at the federal level and provincial level, they recognized the potential value of all these techniques, and also they saw the risk of missing out on this opportunity. So one risk, but also they started seeing how quickly you could see, I don't know if I can point with this, but very large corporations, Microsoft, Google, started setting up headquarters in Montreal and going after researchers where we're doing the research in the university. And so they created this structure, IVADO, as part of a larger strategy to be some sort of like gate between the university and industries that wanted to leverage this technology and also leverage the talent that we had at university. So the interesting thing here is that through this institution being a gate, corporations wanting to access the research had to go through it and not only take, but also give to the research community. So they had to invest in creating more talent, invest in time to work with researchers on projects, not only projects that are creating value immediately, but also projects that had a longer term benefit for the company, but also for the university. So that's just a little bit story. Within 4 years, we saw a lot of things happening. So many companies setting up tent in Montreal, and now instead of just hiring and taking researchers away, the university set up ways for researchers to have a partial implication with the university and the corporations. Like one example is my colleague Israel Pino, who for many years was the head AI at Facebook Research in Montreal, having this dual role at university, but also leading teams at Facebook. And stories like that, there are many. I myself was one of those. I was working with National Bank of Canada in a partial part-time basis, linking university and their teams. So that was one interesting takeaway from this. So IVADO became this institution that it's a bridge. Maybe another interesting thing is the fact that it was recognized that early, and the commitment from the government to fund this in the long run. Maybe it might not seem like much now, but at the time, the commitment was to fund almost $1 billion over 10 years on building this community, which now it's very large. So now it encompasses more than, I think now it's close to 2,000 scientists, because again, the funding that came through from the private industry was used and reinvested in hiring new people, building new teams of students, connecting those teams with industry, and creating many interesting opportunities for undergrads and grads alike. Knowledge transfer. So now that number, it's close to 500 collaborative research projects. And again, I insist, when I mean collaborative research projects, where is a team of 2 or 3 researchers in different departments, so math departments, computer science departments, engineering departments, statistic departments, working together, funded through IVADO and the private sector on problems that were proposed by the companies. Okay, and these projects were, let's say, two-sided. So they had intention of creating value immediately for the company, but also a longer-term objective where we had PhD theses coming out of it, papers coming out of it. So it was an interesting way of leveraging the interest from industry. Outreach. So we had also, that number should be maybe twice now, conferences that were funded through this, but conferences with an applied flavor. I will tell you more about that. And training. Complementary training. So training for the community on specific technical methods, but also in soft skills. So providing the undergrad students and the master students with soft skills that allow them to thrive beyond the academic world, so also in the industry. So that was possible also through this. That's just quickly a picture of this ecosystem. So at the center, IVADO, which is a federating body. Around, we have the actual institutes that do research. So on the top, you see, for instance, the Center of Mathematical Research in Montreal, which is well known in various fields, applied and pure alike. MILA, which is the Artificial Intelligence Institute now, but originally was just the Deep Learning Institute. And then around the next circle, it's partners, academic partners. FINEMEL is one of those logos. FINEMEL is the network that I'm the director of, and it focuses on the finance sector. So IVADO and FINEMEL, together we build the financial services, the vertical of IVADO. But you also see internationally many collaborations with universities in Europe, also in Africa. So it's also an intention of collaborating abroad, not only within Canada. And in the outer circles, then you see the different partners in the industry that we manage to work with. So that's transversal, a cross section of it. Yeah, so you have the Mathematics Research Center, CIREL, which is a center of transport and logistics, University of Montreal, Gerard, it's operations research center, MILA, artificial intelligence, Tech Lab, it's more about engineering and technology. So those are the founding institutes. So maybe here, just maybe on the line of financial services, those are the ones we work with. I personally work with building these relationships. Maybe notorious cases, National Bank. We have a French bank, BNP Paribas, and various insurance companies working with us. And again, each one of those logos represented 5 or 10 projects with many researchers and students working within it. Maybe to wrap up what IVADO is, these are the main components of it. So talent, at the very bottom, we have the students and the researchers that we wanted to leverage and enhance. Then the knowledge, the researcher, and the research that was being made in the university, and then how we could use that to connect with industry. So the knowledge transfer part of it was very important. Transfer happening through research projects, but also through training. Okay, training facilitated by IVADO and its funding, and then reaching out to the community. And here maybe an interesting thing is that by community, a very important component of it was reaching out to the innovation ecosystem within Montreal. So probably the case here is the same, but every university has an incubator most of the time. So students working in engineering, mathematics, computer science, sometimes they have an interest for the entrepreneurship side of things. So how we can use our research and maybe create value otherwise. And so they're incubators. So through IVADO, we also connected a lot with those incubators and helped them connect with actual problems in the industry. And many startups came out of these initiatives. That just to show you the scale of it. So that's Montreal, that's the city. It happened that around that time, Montreal, the University of Montreal was building a new campus here. And then when the shift happened and we started having a more knowledge transfer approach, we saw a lot of other things happening around the campus, actually physically. Universities, not universities, banks setting up labs around so they could have easy access. So that just to show you how transformative this idea was. Can I already skip this? So that's for IVADO. Now, in terms of, like you saw, IVADO, it's about energy, it's about transportation, it's about financial services as well. Under the financial services vertical, that's where FINEMEL, the network that I am director of, play a role. So FINEMEL started in 2016 with the idea or with the realization that the financial services sector was in need of more talent, and talent not only to continue the processes as they are, but also to innovate. Innovate in the sense that banks had, at that time, started to having more and more data, different challenges. And the idea was, how can we leverage all the talent and the research to help them achieve their goals, and through that have like a feedback loop with the university, a way to create more students, more opportunities, and so on. We approach NSERC, which is the National Council of Research in Canada, and this is the institute that actually channels the funding from the government, and IVADO, which was being born at that time. And together we created this network, which is built upon 6 universities in Canada: University of Montreal, HEC, which is a business school, Concordia, Queen's in Ontario, Calgary, and Waterloo, all of which have various programs that are relevant for the financial sector. So not only mathematics, so they have programs in mathematics, actuarial science, computational finance, business analytics, statistics, and we took those programs and those students, and we offered them something else, and that was the goal of FINML. So the goal of FINML is to take those students and propose them a range of training, internship, and opportunities to grow, whether within academia or outside of academia. So that's the founding team of FINML. So these are researchers that represent all of the universities, and they represent also various expertise from operations research, computer science, artificial intelligence. Maybe one notable name there is my colleague Joshua Benvio, who recently got the Alan Turing Prize, so which is the equivalent of the Fields Medal for computer science, one of the founders of deep learning. So together we had this network. The objective was to identify a cohort every year, 2 cohorts every year of students coming from the 6 universities I showed you. Identify them and bring them under the FINML label, and to these cohorts offer them multidisciplinary training on top of their actual program. So these are not courses or training that are part of their program. These are on top of the program. These training are given by the different experts that we have in our network. So training on machine learning, new techniques, but also engineering. How do you set up a pipeline so that you can put in production these kind of things? So it was a very multidisciplinary effort and training. We also offered them the means to connect with industry through these projects that I will tell you more about, collaborative projects. We also offered them internships because within our network, each partner had the obligation to offer internships to the students. But these internships were not just internships that were isolated. So the idea was not just to give an internship here, an internship there. The idea was to have an actual project that had a meaningful and long-term objective, and structured and articulated with the researcher and the partner together. And once we have that project, then we could identify within that project internships that would be meaningful for the researcher and the student and the company. So that was also another key component of it. So having it in a structured way. And so we offered these internships to the students. And then of course, another component was to offer professional development training. So that means soft skills. We noticed that many of our students coming from these hard science programs, sometimes they lack this side of things. So how to communicate the results, understanding of the legal aspects of it, knowing how to interact with other types of profiles within a team. So we try to also give them that, and that we noticed that improved their higher ability. They got higher more because of this side of things. So this is just again to summarize what I said. This program was for undergrads, postgraduate, and also postdoctoral, and they came from a wide range of backgrounds. So economics, mathematics and statistics, business intelligence, quant finance, actuarial science. We had many people from actuarial science. And the structure was, like I said, providing internships, upskilling, training, and professional development. Maybe just to give you a little bit more flavor of what actual trainings we had. So the first one is just saying we identify students. The second line, that's about the workshop we had. The first one is the Ivado workshop on machine learning in finance. So that one we gave it twice a year. We created a program, a curriculum for that workshop that was updated every year. In that workshop was for students, for our students, but also for people from the industry. So there was a high demand. We had like maybe 30 to 40 professionals coming from the partners, so banks and insurance companies, to attend to these workshops along our students. So that was an interesting thing, and we had that every year. We had also a hackathon. So every year we would have a hackathon. So for those of you who are not familiar with the term, so these are like typically 24 hours work where we have a problem proposed by the company, and then the students work non-stop 24 hours modeling, but also putting in place and in production a solution for this. So those are very interesting activities, and the role of the companies was very important because those were hosted at the company offices, and the problem proposed by the company, and the company would also made available to us their engineers, their data sciences, so that we could use their platforms and test our ideas. Another interesting workshop that we had is the CRM and Ivado problem solving workshop. So that's the opposite of the hackathon. So instead of focusing on 24 hours, we had a whole week. Sometimes we had 2, where we had maybe 10 problems every time. Companies would propose a problem. They would come on Monday. They will present the problem. They will bring data. And then on the other side, we had a researcher who was in charge of the problem. There were students, typically 10 to 15 students per problem. And during the week or the 2 weeks, they would work on the problem, brainstorming, doing some modeling with the data and proposing some roadmap towards a solution. Obviously, at the end of the 2 weeks, we didn't have a solution, but at least we have roadmaps, and we had tested many ideas. And the companies like that because that was the starting point of a larger project. So most of the collaborative research projects I told about, they started out from this type of events. So it was the seed for a larger project. We also had career fairs, so the partners would come on campus and actually recruit. Those were some interesting things. On the soft skilling, so we had grant writing courses, commercialization. We had some courses on the AI ethics or data ethics in finance, right? So it's just because we have the data, we don't have the right to use it. So there's some ethical component there. For those of you who are interested on the projects and the things we've been doing over the years, we have a YouTube channel where our students and our researchers, they talk about what they did. So you can take that a look. So I will just spend maybe the last 10 minutes that I have on the specific of the projects. So the transfer knowledge. So there were 3 types of projects. So this is like the traditional matrix of a problem or a project. So difficulty on the Y and innovation on the X. So when you have low difficulty and low innovation, those are like the low hanging fruits. So problems that can be easily or relatively easily solved. We had teams of typically master students working on this, quickly doing proof of concepts and creating value for the company. Then we had more like the wow factor. So innovation is high, but still difficulty in terms of modeling is not that complex. That also gave material for PhDs, theses. And then more complex problems, longer term problems under the how. So we had covered most of these things. To give you a flavor of it, we had, for instance, anomaly detection projects that I will tell you more about with the Stock Exchange of Montreal. And we had I will just let you go through it. It's on electricity trading, on investment. We had a lot of projects, prediction forecasting. We had also interesting projects with blockchain companies and crypto companies, because that's a different game. I mean, it's like having an open book on how hedge fund invests. So when you are in the crypto space, you have more data that we didn't have before, and we're trying to come up with new models to deal with those new views. I will skip this one. This one is interesting. We had a vertical on sustainable finance that grew organically. At the beginning, it was just one project, but then towards the end, we had many projects, many partners interested on how do they integrate ESG factors into their models? What does that mean? ESG, how do you create those metrics? Those were interesting projects. So that's just like an overview of projects. I want to spend maybe 5 minutes on one specific project. So this was with the Montreal Exchange Regulatory Division. So this is an exchange, right? So you have traders, so they have to be buying and selling assets. There's a regulatory division of this stock exchange, because the goal of an exchange is to facilitate trades, right? So any manipulation of prices is forbidden, and so the regulatory division has to oversee all that data and try to see if there are actors trying to manipulate the market. Now, that when this thing happened at the second frequency, that was an easy task. But in the past 7 years, the frequency has increased a lot. So now it happens at the nanosecond. So the regulatory division is having a hard time trying to pick signals and identify bad actors. So we help them do that. I'm running out of time. Okay, so maybe just a picture of what that means. So maybe you, for those of you who are not familiar with how the stock exchange worked, maybe you remember those pictures from the 80s where you had the New York Stock Exchange and a lot of people crying with papers in their hands and trying to find prices. So that's how it works, right? So if somebody wants to buy, it says, I want to buy an asset at this price, and I want to buy this many, and it gives it to an agent. On the other side, you have somebody who wants to sell. Same thing. I want to sell at this price, and then the agent collects those tickets. And then when there's a match, and there's somebody who wants to buy at the same price and somebody who wants to sell at the same price, there's a price that gets created. And the actual price that you see in Google or Yahoo Finance, it's a price that is created every time there's a match between two offers. Now it's computer based. So there's an actual book that registers those offers, and that book changes every nanosecond. And that profile tells you a lot about how the market is going, what are the intentions of the actors in the market. And we were using that data to try to identify delinquent activity. So how did we do that? Maybe I will just give you a flavor of it. We got limit order book data, which is the data I just described. So this register of orders that happen every nanosecond. And the thing is that we wanted to use that to identify things that were not right, like sequence of orders that had the intention not to trade, but just to manipulate the market. To give you an idea, maybe one stock like IBM, every day you have something like 10 million orders. When I mean order is somebody saying, I want to buy at this price, I want to sell at this price. So 10 million a day, just one. Now, 90% of those orders are cancellation orders, because when I send an order and it's standing there, I can remove it anytime. Okay, so that's the mechanics. If I can send a lot of orders on one side, and that kind of bias the book towards one side, but then if I cancel it, I just created the image that there's volume here when actually there's not. Well, 90% of the orders are just cancel orders. So that means that maybe just 10% are actual trades. So it's a task of identifying which one of those were with the intention of manipulating the market or just simply because the price moved away. How did we do that? By creating signals. Okay, because when you have a limit order book, there are very things that we understand very well, like think of options. For those who are in mathematical finance, Options are well understood in the way that how they behave according to the price. So it's relatively easy to take that data and predict if it's an out of the money option, in of the money option, what's the volatility of that option. So it's very easy because you have this data that it's very rich. So it's easy to do that. Now, the idea here was, if I can do that, and I train a model here to predict volatility, for instance, okay, and it's very good. But then when I see that the model, it starts fading, it's not good anymore. So what that means is that probably the activity that I have here, there's something weird with it. It's not normal anymore. Like, it's not normal in the sense that it's not the typical activity that allows me to predict. So we build signals on the error of the prediction. So we predicted something that it's easy to predict, and when we see that the predictor becomes bad, it's because something is wrong with the data. There are other things happening with the data that are noising the signal. And so we build a lot of signals, and actually just to show you numbers. In a very first proof of concept that we did, now this has evolved, we were able to catch delinquent activities that the stock exchange was not able to see, okay? Because they had to go through it almost manually or with very rule-based decisions, right? So when you see this and this together, flag it. Now we had a way to leverage all that data and flag various things. So we were able to successfully identify delinquent activity that was not previously identified. And another important part was that we had very few false positives. I mean, we would only flag maybe 3% of the activity, which is relatively low. Before, when they have rule-based flag detections, probably almost a third of the activity was flagged and they had to be investigated. So this is a successful example, but we had many of these projects. So just to wrap up, through our network, we were able to create projects that in turn created opportunities for students. We trained more than 500 students, and also actual research came out of it. Papers were published by many colleagues, and personally, I had the opportunity to build most of those teams and translate the actual problem that the company had into mathematical objectives that the team had to tackle. So anyway, I hope this was interesting for you, just this story of how we build this and the value that we created for university, but also for the institution. So thank you very much for your time. Okay, a person. So yeah, somebody with a mathematical background. Yeah, well, one of the things we always emphasized was that all this hype about machine learning and AI, at the very foundation of it, it's mathematics and probability and statistics. So people coming with a background in mathematics, that was the objective actually of our program. How can we create short workshops that give them access to the literature, to the latest models, so that the person himself could learn. But now, our program, we had some courses online, but of course there are many courses online now. Harvard, MIT have their own courses online, where somebody with a mathematical background could pick up those things. Yeah, well, Yeah, probably we were biased from the beginning because we worked with the computer science department. So at that time they were using Python, and I think that became the main programming language for this technology. But there are many others. Now I've seen a lot of things happening in Julia or R. Traditionally, actuarial science has been coded in R. So those would be the ones.
Impression, lot of hard work. There's been some recognition that the industry faced this learning techniques. And an increasing gap, or you see that as a threat, that is applying more of these techniques, knowing what the academics are more cautious. How look.
Yeah. No, you're right. There is a gap, and there was a gap at the beginning, and maybe one of the objectives of setting this up was exactly to close that gap. And I think we managed to do that. But maybe with my hat from the private sector, even banks recognize that gap. So I remember many of the projects we put together within the teams, then we never actually, most of them we never put them into production because there was not the governance around the data. So all the questions, banks are very risk averse. So they don't want to put something out there that could potentially harm them. So there's a governance structure, and that means they want to understand the model that they are putting out there, and they didn't understand it. So most of the things that we were building, it never made it to production because there was not that governance validation knowledge internally. Now they're building those, and by building I mean they are hiring experts to challenge from their side internally their model. So there's actually a trend also within the organization to close that gap because they cannot afford not to have it. That's at least in the financial sector. Maybe in other sectors that are more less risk averse and they go more cowboy style and just apply everything. But yeah, it's a good question. Yeah. That's not under my vertical, but Ivado has a AI training pedagogical side of it. So yeah. So if you go to the Ivado website, they have developed MOOCs and other forms of teaching, AI for teaching. Ethics, it's also part of it, but there's another institution that came to life at the same time. It's called OVIA, which is International Observatory of the Societal Impacts of AI and Technology. And under them, you find all the ethics side of this thing. And it's one of the partners of Ivado. But yeah, that also exists. Yeah. Well, Google, it's one of the partners, and it's a closer connection with a specific group within the computer department. Yeah, because Google was one of the first that came on campus, and then they hired some people. Then the university hired them back, and then just kind of set up like a part-time deal with them. But yeah, Google is very present in Montreal. Oh, yeah. There's a lot of conversations in that direction. And I think that's still, I mean, we know what quantum computing can bring. There are already some proof of concepts there. But I think, as far as I know, an application in finance where using a quantum computer actually brings value, it's still to be found. But conversations are happening between groups that have access to quantum computers and groups in finance who try to see, can we find a specific case where having this technology can give you a leverage. The discussion is ongoing. I'm not part of those discussions, but I know that colleagues are trying to identify that use case in finance. But potentially they might be eventually, yeah. Yeah, no, for sure. It's just more about whether in finance there's a problem that needs that type of scaling. I mean, in finance, still, even if you got the nanosecond, still the computers today are able to handle that. So it has to be more about probably optimization of many portfolios that aggregate many things, where that brings an extra value. I don't know. That's a question being discussed. Yeah. Okay, thank you.